Okay, hello everyone, and this is Peiqi from the Chinese University of Hong Kong, and today I'm going to present DistVS, large-scale vector search with compute memory disaggregation. Yeah, first I will introduce the background of vector search. So the workload is we have, a vector search is also known as approximate nearest neighbor search, ANS. So we have query vectors, and we also have a lot of vectors and from the vector datasets. So now we want to retrieve top k nearest vectors from the vector datasets using the query vectors. The traditional method will build an index on the vector datasets to accelerate the search process to avoid the exact vector search. Because if you want to calculate the exact distance for all the vector datasets with the query to obtain the final exact top k result, the computation overhead is very large. So the traditional methods will build an index and to use the approximate method to search on the vector datasets. So the applications are like RAG and recommendation, and also anomalous detection. So for example, in RAG, in the RAG implementation, for each document, so we have a lot of documents in RAG, and now we have a query text, and we want to retrieve a top k nearest documents from the document datasets. So the vector search approach refers to encode each documents into an embedding, and now we encode the query text to an embedding and use the query embedding to search on the embedding datasets, and then to retrieve the top k nearest embedding from the embedding datasets, and then to retrieve the corresponding top k file from the vector datasets, and then return to the RAG application for the following generation. So this is the background for vector search. Yeah, so the SOTA methods for vector search is the graph-based approach. So we have a large vector dataset, and for the graph-based approach, we will first build an index graph on the vector datasets, and to connect the similar node to connect the similar node, and then to form the vector dataset. So upon build a graph based on the vector datasets, the vector search algorithms will starting from the entry points and perform BFS-like traversal on the vector datasets. And it will traverse on the datasets and calculate the distance between the node and the query on the whole path in the graph traverse. And after the graph traversal, it will return the final top k result that by calculating the query vectors and the vectors in the datasets to calculate the distance between them. Yeah, when the data becomes larger, for example, we have 1 billion nodes in the vector dataset, and each vectors are in high dimensional, for example, 1024. And in this case, if we store everything on memory, the memory overhead may become very large, and we cannot solve that. So for disk, so two-tier ANS index are proposed that it can offload most of the data to the disk. So now we have a two-tier. The first tier is in memory, and the second tier is on disk. So in memory, we will store compressed vectors in the memory for the whole data set, and using some vector quantization algorithms, for example, like product quantization Peiqi. Yeah, and in the following of the talk, I will use Peiqi to represent the compressed vectors. And in memory, they will store the compressed vector, and on the disk, it will store the exact vector and the graph data, because we build a graph on the vector data set. So for each node, we have the exact vector, and we also have the graph data. So for the traverse, for the search process, we will, for example, starting from the entry point, and then to conduct the graph search on the graph traverse on the search. And for when a node becomes the candidate to be searched, and it will load the exact vector and the graph data from the disk and calculate the approximate distance between the compressed vector and the query vectors, and use the approximate distance to guide the search, to guide the traverse. And after the traverse, it will use the exact distance to calculate the final top k result to be returned. Yeah, so here I propose several index algorithm. The first one is disaggregation, and the second one is starting. So for disaggregation, it will store the nodes, exact distance, and graph data on the same disk page. So by this approach, we only need one disk access, then it can load for both exact vector and the graph data from disk. And starting build upon disaggregation, it reorder the disk layout and to increase the data locality on the disk page. Yeah, this is the existing system for the two-tier ANS index. Yeah, so now we found several challenges for this two-tier AN index. The first one is the two-tier index is still need a large memory consumption. And this is because the index requires to store the whole compressed vector on the memory. So this may consume 10% of the overall space of the overall data set. And this is because we can see the figure here. The x-axis represents the Peiqi compression factors. Higher Peiqi compression factors represents we can use lower memory to store the compressed vector, but the compressed vector are become less inaccurate. So the y-axis is the throughput and the number of node visits during the graph traverse. So we can find that with increased Peiqi compression factor, the throughput first increase and then decrease. And for the decrease, this is because if we reduce the accuracy of the compressed vectors, the approximate distance become inaccurate. So the graph traverse have to search for have to visit for more nodes, and then can achieve the same accuracy, which is also known as the recurse. And because we visit for more nodes, and then we introduce more disk access and distance calculation, and that will reduce the overall throughput. So we still have to keep a high precision compression. We still have to keep a low compression factor, also known as the high accuracy vectors on memory. So we cannot compress the vectors in very high compression factors. So the second challenge is although we have kept a set of the data in memory, we still have a very heavy disk access overhead. This is because both the graph data and the exact vector are stored on the disk. So for each graph traverse, the search iteration requires one disk access to load the graph data from disk, and the disk access will dominate the overall query time. And we can see the figure here. The x-axis represents different data sets, and we compare on both disaggregation and the starting system. And the y-axis represents the time decomposition of the compute time and the disk access time. So we can find that for both data sets, the disk access time still dominates the overall calculation time. And the further challenge is that we found that for the two-tier index, it needs to store the compressed data on memory, and need the SSD to store the exact vector and the graph data. So everything is kept inside one standalone server, and this is very hard to scale up. If we scale, we have to duplicate everything. We have to duplicate the compressed vector into different memory, and we have to duplicate the graph data and the exact vector into different SSD in different servers. So this is very hard to scale up. So we found that we have several challenges for this kind of two-tier AN index. The first one is large memory consumption. The second one is heavy disk access overhead. And finally is the low scalability. And this is all because we couple the execution on the standalone servers. So for DistVS, we propose to disaggregate everything. We disaggregate the compute server, the memory server, and the storing server. And we disaggregate everything into different servers. And next, the question is, how does we disaggregate them? Yeah, so then we propose several observations based on this challenge and to propose our system design. The first one is that we found that the demand for the exact vector is less than the graph data. So for the disk-based system, they store the nodes exact vector and the graph data together on the same disk page. So during the searching, both graph data and the exact vector will be accessed together within one disk access. But however, we found that the exact vectors are only used for the final re-ranking, and the graph data are only used during the searching. So actually, the demands to the exact vector and the graph data are not the same. Actually, we found that the graph data is required more during the search, because for each iteration, it requires to read the disk to obtain the graph data, but the exact vector are only used for the re-ranking phrase. So actually, we can promote the we can store the graph data on the memory rather than store them on disk. So this is the first observation. And the second observation is that although we found that if we use very low precision PQ, it will reduce the overall accuracy. But the low precision PQ, it still can provide some of the guidance for searching on the graph. So driven by this design, we think that whether we can use 2 precision of PQ during the searching. So we can use cross to fine distance estimation to guide our search rather than only use 1 precision of the PQ compression factors. So next, we propose our press algorithm. So the key idea is that in our algorithm, we can use 3 precision. So we use 2 precision of PQ and 1 precision for the exact vectors. So we use the low precision PQ for search on the graph, and we use a high precision PQ to select the candidate for next iteration. And finally, we use the exact vectors, also known as the full vector, used for the final re-ranking phrase. So the algorithm will process like, for each iteration, it will use the low precision PQ to expand the neighbors and to calculate the low precision distance between its neighbors, and then select a portion of high ranking nodes in the low precision PQ and use them to calculate the high precision distance, and then to select the candidate, which is known as the candidates for next iterations, and using the high precision PQ. And after the traverse, finally, it will use the exact vectors to calculate the final top K result. And next is our DistVS system design, and we propose to disaggregate the press algorithm. So the dist system, for the search algorithm, we use 3 precision, the low precision PQ, high precision PQ, and exact vectors. And for the DistVS system, we store them in the compute server, the memory server, and the storage server, respectively. So in the compute server, we will store the low precision PQ and only. And in the memory server, it will store the high precision PQ and also store the index graph. And finally, for the storage server, it will store the full vectors. So for the search process, first we have a query entered to the compute server. The compute server have compute thread to calculate the low precision PQ between the data. And next, it will send the high-ranking node's ID to the memory server, and the memory thread will calculate the high precision distance between these nodes and the high precision PQ. And next, it will select the candidate nodes and extract their graph data, extract their adjacent list from the graph data, and to send back to the compute thread. So this is the iteration between the compute server and the memory server. And finally, if the memory thread found that, okay, there's no more nodes could be calculated, and the search iteration can be ceased. So the memory server will send the top ranking nodes to the storage server, and the re-ranking thread in the storage server will calculate the re-ranking phrase and to calculate the final distance between the full vectors and the query vectors, and finally return the overall result. And our evaluation showed that our press algorithm can, using the press algorithm can achieve similar performance as using only high precision PQ, and much better than using low precision PQ. Yeah, that is because we use high precision PQ to calculate a portion of nodes, and most of the distance calculation are conducted using the low precision PQ in the compute server. So most of the calculation occurs in the compute server, and a small portion of the calculation occurs on the memory server, and very few calculation happens on the storage servers. And based on the DistVS system, we propose several system optimization on that. The first one is the iteration-based asynchronous execution. So because our compute server and the memory server require communication, so after the compute thread sends the message to the memory server, the compute thread can immediately to working on another query. So we use the coroutine to switch the, we use the pipeline parallelism to pipeline the execution for different requests in the compute thread and also in the memory thread to avoid the CPU idle waiting for the remote response. And second is the continuous RDMA IO batching. Because our communication between the memory server and the compute servers are only required to send the node IDs and the graph data. So actually the data is very few, maybe like several hundreds of bytes. Yeah. So if we only send such small message, it will make the RDMA NIC channel become the over bottleneck because it still requires RDMA transfer time, and if we have a lot of message, they will be blocked there. So we use the RDMA IO batching to batch use the communication thread to batch the small message into a larger one. Yeah. And finally, it's our evaluation. We conduct our evaluation on 3 systems, DistVS, Starling, and Peiqi on 5 datasets. And the size of the datasets range from 1 billion nodes to 100 million nodes, and the dimensions goes from 96 to 768. And for the baseline system, we conduct in 5 independent or standalone servers. And for our system, we conduct on 4 compute servers and 1 memory servers. And this is the overall performance. We have 5 data sets, and the x-axis is the recall, and the y-axis is the throughput and the latency. So we can find that DistVS improved the throughput, outperform all baselines for the throughput, and improved throughput over 114% by DCN and 70% by Peiqi. And DCN's latency also performs similar latency compared to these baselines. And finally, it's our evaluation. We found that our system can use less memory compared to this baseline system because we use one memory server and several compute servers. And each compute server only need to contain a small memory portions. But for the baseline system, they still need to store most of things on their local memory. And finally, it's our conclusion. We identified the main bottleneck for DistVS is the high memory overhead and the costly disk I/O. And we observed that compute memory disaggregation architecture can resolve the problems. And next, we designed the DistVS system, which features a 3-tier storage layout and the press algorithm with free precision for the searching. And next, we introduced several system optimization, including asynchronous execution and I/O batching to improve the overall performance. And finally, we evaluate the DistVS can outperform all the baselines and verify our designs. Yeah, and that's all for the talk. And thanks for listening. And any questions?